dilation corresponds to the phenomenon whereby an observer perceives that another observer's clock, physically identical to his own clock, but which is moving away, walks slower than his own. That is, the time recorded on the clock of a stationary observer is different from another, which is moving. The first static observer's perception is that time walks slower for the moving clock. However, this is true only in the frame of the still observer. In the absence of acceleration, paradoxically, the other observer will also see the clock in the previous frame of reference, previously immobile, and now moving relatively, walking slower than his own clock. From the perspective of any static observer, next to either of the two frames of reference, if the two clocks are synchronized and kept together without relative motion, they will neither lag nor advance, one in relation to the other. The difference in the measurement of time between the static referential and that which is in movement is due, according to the theory of relativity, to the dilation of time. The time intervals marked by an observer at rest are always greater than the time intervals marked by a moving observer. This becomes more sensitive in the case of speeds close to the speed of light. The only absolute quantity in any frame of reference is the speed of light. Although the ubiquity of light is not a prediction of physics, one might think that light would possess these characteristics. In other words, being a magnitude that does not depend on the frame of reference occupied by the observer, light could be, sooner or later, everywhere in space at the same time. We say that time will pass at the same rate for two observers if both experience the simultaneity of events. Their clocks do not change, in this case, marking equal time modules. For this to happen, the two observers must be at rest with respect to themselves. Therefore, understanding time is closely linked to the idea of simultaneity. Observers that move relatively to each other cannot have their clocks synchronized, given that the time intervals measured by them are not the same. Still, according to the theory of special relativity, and as a direct consequence of the postulate that the speed of light is the same when measured from any referential, the measurement of distances from different referentials is also affected. That is, while time dilates, space contracts in a complementary way. To exemplify, let's imagine an observer on Earth and another piloting a spacecraft. We call length the distance between these 2 points, which will be measured from the reference frame at rest. The spaceship will be the other inertial frame, which will be moving relative to the first. What we see with this result is that the distance measured by the observer who was on Earth is greater than that measured by the astronaut aboard his spacecraft. Therefore, in addition to time dilation, the astronaut will have experienced space contraction. Thus, in the spacecraft's frame of reference, the astronaut's journey took less time than that measured by those on Earth. Consequently, the trip made by the astronaut must have a distance smaller than that measured by an observer here on Earth. It is necessary to note the relative character of the movement, since the contraction of space affects everything contained in it, being also relative. There is no absolute measure for the length of space. In all these observations, contained in the theory of relativity, the importance of the observer's point of view, which analyzes the movement around him, stands out. Who can safely say that these events of time dilation and space contraction would exist if the observer did not exist? One thing is certain. There is no physics treatise in which it is stated that the observer on Earth or in the spaceship could experience a contraction of time nor a dilation of space. Similarly, no stationary clock could show time passing faster in the other moving reference frame, or that the space around the ship could have suffered an expansion in its length. Whenever one thinks about the relative movement between these two mentioned references, space will necessarily be contracting and time expanding. For this reason, in images of the universe we have raised counterpoints to inflationary theories, as they predict that the relative movement between distant galaxies would occur due to the expansion of the space that welcomes them. For the images of the universe project, the galaxies seem to move away from each other, not absolutely, but due to the contraction of space and the dilation of time. These events, therefore, would involve the point of view of the isolated observer. If we could not count on these changes in the geometry of space to influence the passage of time, the galaxies themselves would remain stationary. If, like the observer, they were conscious and could analyze the relative motion around the other galaxies around them, would experience time dilation, or the contraction of space. As long as they were moving away from each other with ever-increasing speeds, there would be no absolute movement between them. This alternative interpretation allows us to think that the galaxies seem to be moving away from each other because the space around them would be losing curvature and contracting. If space was increasing its curvature as it stretched or expanded, the observer could not know this directly due to the simultaneous contraction of time. It would be necessary for the arrow of time to be inverted and space to start contracting and losing curvature. Time, previously contracted during expansion, would have started to dilate in an apparently continuous way, accompanied by the contraction of the length of space. As expansion cannot be directly assessed or depends on remote tracking of information, it does not exist in practice. Or, at best, it would be taking place somewhere outside of space-time. Within the observable universe, time could only expand if space contracted. The reverse could not be predicted. The expansion of space would have to be accompanied by an increase in potential energy. Its contraction, on the other hand, would always be accompanied by a drop in that energy or an increase in kinetic energy. Potential energy could not increase in spacetime because the only known force acting on the astronomical scale is gravity. It is always accompanied by a drop in potential energy and an increase in kinetic energy. For better understanding, think of space as a spring. Potential energy increases when this spring stretches, generating tension between its ends. Something similar should happen in the expansionary phase of the universe. If the spring were to contract, or if it were let free to relax, the event would be accompanied by acceleration and a fall in potential energy. Time would dilate. This is what seems to happen inside space-time, where space is always contracting and never expanding. We can conclude that the dilation of time linked to the contraction of space is what would allow us to see the apparent expansion of the universe as an event that would have occurred in our past. Since we need the cosmic microwave background radiation to describe the expansion, it could only be evaluated indirectly. That is, the expansion of the universe always presents itself to us, late or out of its own time.